Now we are live in YouTube.
Okay. Okay. Hello and welcome to Digital Futures. Welcome to our next tutorial session for the year 2022. We're delighted to have hello. Yeah, we're delighted to have Betty Chavez joining us for welcome to sorry for that. I think I got disconnected there. Yes. We're delighted to have Betty Chavez joining us today for this amazing session on evolutionary behaviors with C# basic in Grasshopper, Grasshopper for Rhino. Just a reminder, all our tutorials are available on our YouTube archive material under our YouTube channel, including the recently or the last week's session on X-School technology. We also have our deadlines for the CDRF or CDRF conference on hybrid intelligence extended to 17th of January. If all those who have registered and have are yet to present their abstract, the deadline is in 2 days. Next week, we also have our second in the series of our Farsi language sessions on 21st of Jan. The session will be covering context, interpretation, and design in the region, in the Farsi region. And next Saturday, at the same time, we will also have another session on new hybridities, Latin America. And the Sunday after that is a continuation to our collaboration with the FIU University and Digital Futures Doctoral Consortium series hosted by Professor Neil Litch. Without further ado, I would like to start with today's session. And I would like to invite Betty Chavez. Before we begin, I'll take the opportunity to just give a few introductory words to Betty. She is an architect from Pontifical Catholic University of Peru, winner of President of Republic Scholarship from Peruvian government in 2019, a master's in architectural design and with mention in multi-materials by the Bartlett School of Architecture, UCL London. She is the co-creator of Metablast 3D printed multi-polymers design project and a teacher of final career projects and research in the architecture and urbanism faculty of Pontifical Catholic University of Peru. She is an independent designer and researcher and founder of experimental design laboratory called Ladu B Design Lab. Without further ado, Betty, the screen is all yours.
Hi, everyone. Can you hear me well?
Yes.
Perfect. Hi, everyone. I'm very excited to be here with you, sharing this tutorial that is called Basics of C# Evolutionary Behaviors. A bit of me, a presentation, despite I've received a very good welcome this morning. As I was announced, I am an architect with a master in architectural design. I'm currently a professor at the Pontifical Catholic University of Peru, thesis project and research, advanced research. And I have a small laboratory of design, experimental design with computational tools and new technologies called Ladobe Design Lab with an Instagram page, and you can take a look if you like. It's a bit of fun there. So let's start with the tutorial, because for those who haven't coded before, maybe it's going to be a bit exhausting. I will take a bit of time. So let's begin quickly. Both concepts are main for this presentation is evolution and behaviors. And how I got in touch with these concepts through my research in design. I'm very interested in many types of design, methodologies and processes. So I wanted to get out of what is human normal methodologies of design that I find very linear, and they are very static to my eyes. Like, they are not able to transform through time, to interact with new conditions. So they easily become obsolete in time. So I wanted to look out of this type of designing, and I didn't have to look very far away. Nature is very overwhelming around us, and their characteristic for designing objects and elements is very different. It's based in optimization of material, as we can see in the pictures, and also the nature design behaviors. So elements in nature are able to interact with their environment, transform, respond, and act through the many circumstances that occurs in it. Like, for example, this tree, like, it changes through seasons. And another concept very interesting inside natural design or design from nature is evolution. I want to say that this concept is very, very complex and well more open than what we are going to see today. But basically, what evolution says is the characteristic of nature of creating many iterations of one element, pick the most optimal one that would survive through generations. So we achieve more optimum design through time. I want also say that human design is also very inspired in nature. That's a very positive characteristic. We are always aiming to reach the same amount of efficiency and optimization. And we also have our own evolutionary process of the elements we create, but these elements by themselves, they remain static. But through time, we can say our creations evolve. But that's the more wide characteristic of the concept of evolution. We are going to focus just in what element, the properties of one element to interact with their environment. And we have used these evolutionary behaviors for architecture. For example, here there is an algorithm that optimizes paths that connects entrances with train platforms. And through this, we can run several simulations and pick the most optimal ones. Okay, so we are going to dive into the concept of iteration that is our center today. Iteration is a very interesting characteristic because it allows us to go through some set of instructions several times. And it depends of if we change the context for every iteration, we can have different results. Or if we iterate through the same element, but within a period of time, with time variation, we can create motion or transformation. Here there is example of great industrial designer Theo Jansen with the project Stand-Beast. And we have at the left simple structure, at the right many iterations of the same structure, and in the middle how if we overlap all these iterations, we create motion. So this is the result. If you're interested in generative design, this is a mandatory lecture and research project. So we are going to dive into coding because we need to move fast through this. If you haven't coded before, maybe this is going to be hard at the beginning and slow because we have to get into the basics of C#. We need to learn how to use the tool first before coding any behavior. So the aims in general for this tutorial are basically to make an introduction to an advanced level of using Grasshopper through scripting. Maybe you all use already Grasshopper, that is a type of coding, more graphic, but we can also get deeper through scripting, making an introduction to designing behaviors, improve your general programming skill, and the particular aims is just get the basics of coding in C#, make some vectorial operations. For these vectorial operations, if you are not in touch or you don't have this very fresh in your memory, don't worry, you can revise some vectorial operation theory and you will catch up immediately. Probably in these parts, we are going to go very fast, just copy the functions and that's it. Then we are going to learn how to use loops to iterate, to play with this iteration capability of coding. And we also aim to create some simple interactions of elements in the canvas. Okay, next. In Grasshopper, there are many types of scripting languages like Java, like VB, and C#. Today, we are going to dive into C#. But I don't believe anyone is better than the other. It's just a personal preference. And I use it because I think it's mature, it's well documented, the community is large, and especially because it's like it uses explicit scripting. This means that you cannot assume things, or the computer will not assume things. At least you are very explicit scripting and giving instructions, and that's very useful in terms of debugging or not making mistakes. This is how this works. It's very, very fast, I will say. Normally, we'll just, in Grasshopper, we just connect components and then these are transformed in machine's instructions, but we are going to go one step behind. We are going to script the component, then it transforms in a component and we will execute the code later. Very good. This is the initial theory about the language we are going to use. So first of all, we need to learn the basics. Here we have a screenshot of our component of C# in Grasshopper. So if we go to Grasshopper right now, here I have my my two tabs, Rhino at the right and Grasshopper at the left. If we open
we cannot see your Rhino-Grasshopper screen, Betty.
Okay.
Yeah,
sorry.
we still see the presentation. Yeah, no problem. Yeah.
What about now?
Yes, perfect. Yeah.
Perfect. Okay, so we have arrived into our Grasshopper canvas with the three-dimensional space of Rhino. Okay, so if we double click, we can open a C# component. We can also find it in the mathematics, the math menu here, and there you have the C# component at the top. So we have two moments in C#, right? We have at the right the inputs. We are gonna get closer. We got some inputs, and at the left one the inputs, and the right the outputs. This is the inputs are to insert information from the outside of the script to the script so we can operate with them, and the outputs are to extract information from the script to the three-dimensional space of Rhino. So if we return to the presentation, can you see the presentation now?
Yes.
Perfect. So this is what I was saying, the input and the output. If we double click this component, we can see this screen. Please don't get scared of this. I know it's a lot of code. Don't get traumatized by this interface. I know it's not very friendly. If you are in Windows like me, you're going to see this. If you are in Mac, you are going to have a more familiar interface. You're going to just have two blank space, one above the other. So I will explain how you can use these spaces. The first blank space here is where we are going to script the code. We are going to write the code for running. And you can notice because there is a script that says private void run script And inside parentheses, we have the inputs that we saw previously, this X and Y, we saw them inside the parentheses, and also a ref object A that we can see in the output, right? So these are the elements that we can use inside this code. And where we are going to write the code? In this blank space. Then the secondary blank space is just to write additional resources that you can use in the main code. This part, the code that you write here is not going to be run when you execute the component, but it's for elements that you want to define previously supported code. So in Mac, both blank spaces are exactly these two spaces. The top blank space is where you have to write the code you want to execute. And the below, if you want to write some supportive additional code, for example, you want to set a function that doesn't exist, that you're going to use many times in the code, you can write it down so the machine says, okay, this function exists. But we are not going to focus on this secondary blank space. We're just going to write the code directly on the run script space. Okay, so don't get scared. This is where we are going to work in the first blank space. Don't worry about the extra code is in the screen. We cannot even modify that. That's how the component understand has to run whatever you write. So perfect. Let's move into the basic of coding in C#. This is a very important concept for coding. If you already work with algorithms, you're probably familiarized with this concept of variable. If you are not, variables are symbols that store different types of data. Okay, they can store whatever you want, but they store data of a certain type. This is why I say C# is an explicit and static typing. It's because for starting a variable, or to say to the computer that I'm gonna define a variable to work with, I need first to say what type of information I'm gonna store in my variable. So we can see that to define a variable, to initialize a variable, we have a special syntaxes that is composed in these parts. First, we have the variable type. These are the three most common and used types of variable in scripting. The first are numbers that are integers, and the variable type to define it is int. Then we can define variables that are doubles, that means decimal numbers, or strings that mean strings of words, like a chain of letters, basically. So these three are three different types of variable. Okay, so to declare a variable, we need the first to write the type of the information we're going to store. Then we can assign any name to this variable. In this case, I put just a letter A, and then equal, and the value that's going to be stored inside this variable. So here I have declared three different variables. One is an integer with the int, the variable type that is int, then the name of the variable A, and then equal to 5. The next is a double, a decimal number, so I declare it as a double, then the name B, and the content that is 550, and then a string C containing the word or the string of letters hello world. After I declare my variables, I can operate with them. For example, I have already declared the variable B with 550, and later I want to change the value, and I just have to say that it's equal to a different number. I don't have to declare it again to say it's a double, because the computer remembers that it is a double. So if we go to the Rhino interface, we can get into our C# component, and we can start declaring some variables. So we copy the information we saw. We want to declare an integer. We name it int A. A is the name of the variable, int is the type of the information that A will store, and I will say 5 because it's an integer number. Then I will declare a double. It will be B, and it's a decimal number, so I will write decimals, and C, that will be a string. Every string of letters should be inside a double quotation, okay? So the computer understands is a string, like a bunch, an array of letters. So I will write hello world. Hello world. And okay, I will put okay, but I cannot see anything of that outside my component. If I connect it, I cannot see anything, right? To see everything out here, I have to relate this variable to one of my outputs. In this case, I have an output A that that is on my component. So I could just say A equal to, let's say A, my variable A. So now when I connect it to a panel, I can see the variable A. And as I said, once the variable is declared, you can change the value. So let's say A now is not going to be 5, it's going to be 4. And we can see it has changed. Something I was forgetting to tell you is that to end every statement in coding, especially in C#, there are other types of language when you don't need to do this, or you don't need to do this, is that to say to the computer that you have finished to declaring something or writing a function or writing in general an instruction, you have to end it with a semicolon. This is how the computer knows, okay, this is one instructions, let's go to the other. Okay, so this is very, very important. If you forget about this, you're going to have some errors. Perfect. So the first exercise we're going to do is to declare 2 variables and try to add them, like operate with the variables. Right now we have 3 variables we have declared, but we are just seeing out there the variable itself. We are not operating them. If we want to operate with them, we can do it just like common numbers because they store numbers. So we can add, make an addition like this, for example, A, my output 8 will show me the addition of my variable A and B. So here we have the final result. And if we change the value of A, for example, 20, we can see how the value is immediately updated. Okay, this is very important for you to learn the syntaxes of how to declare a variable and how to operate with them. Maybe some of you will wonder if we can operate integers with doubles. Yes, we can. We can operate both of them because both are quantities, both are numbers. And obviously, if you are adding a double, probably your result will be also a double because you're adding decimals. But we cannot operate with the strings because these are not values. We are not going to use strings for today's tutorial, so we will erase them. So the next part of the exercise today is to add 2 external values. Until now, we have created some variables inside the code and we have added them together to get a final result. But we can also operate external values, values that we plug into our component. So let's go in. And here there are the inputs. How we pass the information from the outside to the inside of the component. We have to do exactly the same. We have to declare the variable. Here, the variable already comes with some names, X and Y, that if you right-click on it, you can change the name for any name you want to give to your variable. I will leave it as an X. But we also need to say to the computer what type of information this variable is going to pass into my component. And how we do this, we go down here to type hint. And here we have a bunch of type of information we can plug into our component. Today, we are just gonna declare a double value. And y is gonna be also a double value. So I'm gonna say to the machine is a double. I will double click to add a number. I will just write a decimal number. A slider will immediately appear. I will copy. We have two decimal numbers. I will add them to the C# plugin component. And when I go in here up in the private void run script function, we can see that there are two declared variables that we can use inside our code, double X and double Y. They already have a value that is being given from the outside of the component. So what we can do now, we can have another output. I will name it B, and I will operate with these two external values. So B is going to be equal to X plus Y. Okay, so I have an error because I don't have an output named B. For adding and subtracting or removing inputs or outputs, here, if you get very close, you're going to get a plus and a minus symbol where you can add more inputs or outputs or remove them. So now that I augmented my outputs and I placed B there, I can connect a panel and see that effectively my B is the result of the sum of X and Y. And as they are external values, I can modify them from the output, from the outside of the script, and I can see how immediately updates the result as long as I change the X or Y value. So this is extremely interesting because it allows me to control the results and change the result according to the outside condition of the script, right? Perfect. So we have achieved our first exercise. These are very simple exercises. The 3 or 4 first exercises are just to learn how to use C#, and we will move to behaviors later. So then we have different types of data type, not only numbers or letters, right? C# for Grasshopper has already a library of types of data that you can create, that you can visualize on Rhino. Normally, these are geometry data types, like, for example, points in the three-dimensional space, vectors in the three-dimensional space. So how do we create these data types? I will show you the structure right now, but I want to comment that there is a page, a web page called Rhino Common Library, where you can consult how to create different types of geometry data types inside your scripting. If we go to the browser, I have search. You can just search in Google Rhino Common Library, and you're going to get into this this web page. And here you can consult how to create Rhino objects, how to I don't know, give many instructions. So what to do, operator, methods, functions, whatever already set codes are installed in our program. So here, for example, I went to geometry in Rhino, and I have the instruction of how to create a curve, how to create hatch, different types of geometry, lines, points. It's very hard to understand the structure of this page, but if you have a particular question, you can just write here in the browser, so you can get the instruction very easily. So, okay, let's return to a point 3D. We are going to work with points in this session. So how do we declare a point and construct a point in this space? This is the syntax. The first part is exactly the same as what we have done with simple variables. We have to say first what the type of data we are going to store in a variable and put a name for this variable. So the first is the type of the information, that is a point 3D. This is the command for creating a point 3D. And then a name. Here I just put a simple A. and then I put equal. And here is where we are going to create this point 3D that's going to be stored inside a variable. Okay, and how we create a geometry element in Grasshopper with the word new. This is the syntax that we have to remember, new, then point 3D, and we put open and close brackets. What goes inside brackets? Some kind of information we need to create this point 3D. The information we need to create every geometry data type, we can consult it in Rhino Common. But here, I will make it simple. What a point 3D needs to be constructed are coordinates, okay? X, Y, and Z, to know the position, the right position of the point. And this point will be stored in the variable A. So we are gonna go to the Rhino canvas to construct a three-dimensional point. We are gonna open a different component of C#. We are gonna get in, and here we are gonna construct a point 3D. So what's the syntaxes? We have to say the type of information that is a point 3D, and then we give it a name. This is gonna be my point. You can give the name that you want, that you prefer, but I'm gonna use my point. And now I have to construct a point to store it in this variable. So I will say new point 3D bracket and bracket. Okay. And to extract this point and be able to see it on my Rhino three-dimensional space, I have to assign this point to my output. That is A. A will be equal to my point. Perfect. So I put OK. And we can see here a point appear in the 0, 0, 0. This is what happens when we don't give or provide the coordinates for the point. Immediately, the computer assumes that it's 0, 0, 0. There is another way to construct a point that is giving yourself, giving the coordinates that you want for the point. Here, I have set 0, 1, 2. And there is another way to declare a point that is passing the information of a point that I have already declared. For example, I'm going to create a point 3D named C, but I'm not going to construct a point from 0 because I want to copy the information of a point that I have already created. So I just put equal B, that I know is a point that already exists, and the computer just copy the information of this point. These are the three types to declare a point 3D. Perfect. So we already created this point. So the only thing that I'm going to add to the exercise is to give the coordinates. So what happens if we give a coordinate here? I put 0, dot 0, comma, and here you can see how the script editor helps you, telling you that you need to put a double for X, Y, and Z. So you have a guidance here that will remind you how to fill these brackets. So I will put 2, and I will put 3. Perfect, and we will see how the point has moved its position, and we can create many, right? Many of them. I will copy this. I will put, I have to put another name because it's another point. My second point, I will change the information of the coordinates so I can see it separately. And I will have another output, V. Second point, I put OK, and I don't have the output yet, but as soon as I create my output, both points will appear in the canvas. Okay, creating points is fun. You can play with this as much as you want. So I will keep moving through the tutorial, but I recommend you to practice all these constructions later. Perfect. So we are going to go to, we already know how to declare elements inside the C# component and to see them in the Rhino canvas. But well, if we want to operate or establish other types of conditions, make more complex things, so we have different statements that we can use inside the script to start operating these values that are loose values until now. One of these statements is the if statement. This is very intuitive, so I think this won't be hard. And this is the syntax to create a conditional inside a script. We use the word if, and inside brackets, we put the condition we want to meet to execute a piece of code. And right after the brackets, we open curly brackets, and inside these curly brackets, we write what we want to execute if this condition is true. And if we want to create an order to do or some instruction to do in case this is false, we can use the command else, just like appears here in the screen. So first we have put if x is larger than y, we are going to execute this function. The function print with capital letter and brackets, what it's going to do is going to pull out whatever you want out of the component as a string using the output. If we go to our component here, we can see that we always have this first output. This is for you to extract any kind of a string or sentence or words outside the script of the component. And for that, to pass the information through this output, we use the function print. Sorry, I'm going to close this. And okay. So I'm going to print out, if x is larger than y, I'm going to print out this sentence, x is larger than y. And if this is false, I will print x is smaller than y. I'm going to pass this to the Grasshopper so we can see it in real time. So C#. I'm going to connect this so we can visualize it. Okay, so first I'm going to declare these two variables. I think I'm just going to copy this first component because it has the variables already declared. I'm going to get into, and I'm going to write the if statement, okay? So if x is larger than y, curly bracket, and I have to write here the instruction, what to do if this is true. Print, what I'm going to print? I'm going to print a sentence that says x is larger than y. Perfect. Okay, I just have to put okay here, and I put a panel to visualize the information. Okay, there is some problem here. Okay. Perfect. So now x is larger than y. And I can manipulate this. Okay, when x is smaller than y, it's not doing anything because they don't have, it doesn't have an instruction. But if I want to give an instruction, I can use the command else. Curly bracket, and then we put a different instruction. Print x is smaller than y. Perfect. Semicolon to finish the sentence. So, okay, when x is smaller, I have this statement. When x is larger, I have this statement. So this is very intuitive, right? How to use if a statement is a simple conditional. This is another way to use simple conditionals in a way that helps us to remove or reduce precedence. This is used in case, for example, we are going to test many things, many elements, and we want to test if the condition is met several times, and if this is met or not, we have to execute a code. So how this continue works. For example, if X is larger than Y, if this condition is true, we don't execute the code that is below. We continue checking the next iteration of values we want to compare. But if this condition is false, we execute the code that is below. This is very helpful, as I said, to when we are repeating this conditional to test many elements. So we don't want to write else and don't do anything or overscript our code. Here, this word continue just help us to, if this is true, go to the next iteration and this estimate the code we have written below. We're going to use this later, so don't worry if you don't got it right now. In example, maybe it's going to be easier. And the other function we have to learn, because this is something you need to memorize, this kind of syntaxes we have to memorize. Don't worry for now, because I'm going to be writing everything with you inside the component. You can just copy it and later review the tutorial so you can dive into the reason why it's like this and practice more. So the next statement we have to learn is the for loop. What is a for loop? A for loop is a statement that helps us repeating a piece of code a determinate number of times. Okay, so if we want to execute this action many times, we don't have to write it, I don't know, 10 times, 100 times in the code. We can just use these commands, these statements, to define how many times we want to repeat it, and the computer will understand that we want to repeat it several times. So this is the syntaxes. I know it's very familiar and it's not very gentle in general for our mind, our brain, but you get used to it. And this is how you write it. First, you write the for word to start the for loop. Then you have some instructions inside a normal bracket, and then you open curly bracket, and inside your curly bracket, you type whatever code you want to repeat. And what is inside these normal brackets right after for command? We have 3 statements inside this bracket. And in these statements needs to tell the machine or provide some parameters and constraints for the machine to understand that it has to be repeated a number of times. So at the beginning, we have the first statement that is that we need to define and declare a count variable. Here, the convention said the for loop starts with I, but you can name it as you wish. I'm going to use the convention. So it's an integer named I, and set the initial value for the repetitions. I will start in my iteration number 0. That is my first iteration. Perfect. And we separate these 3 statements by semicolon. Why? Because these are 3 different statements. These are not 3 characteristics, like, for example, coordinates of a point. There are X, Y, and Z. No, these are 3 different instructions that normally will be in different rows. But here we have to compile them inside the brackets. So we use semicolon because there are 3 different statements. The second statement is where we need to set the number of repetition for this code. The amount of time this code will be executed. So what we say I is always less than the amount of times we want to repeat the code. Here I put 10, you can put 100, 20, 50, whatever you want. And why less? Because the iterations always start in 0. This means from 0 to 9, we are going to have 10 steps. So the condition of the 10 repetitions is going to be me. And the next statement, the third one, that is one of the most important, is that per every iteration, my variable I will be increased by 1. This helps me because every time I repeat, I will change from 0 to 1, then to 2, then to 3. And when it reaches 9, it will stop. Because if you add 1 more, you will, the statement of repetition that we said before, that is I is smaller than 10, will be false. And that cannot be possible. This is a statement. I is always smaller than 10. So the combination of the second and the third statement inside the for loop help me to tell the machine where, when, and where to stop to looping this code I want to repeat. I know it's tricky. I know it's very unfamiliar to our normal communication, but this is how computers understand what we want to do. So for example, here there is my for loop that I have written. I want to run a for loop for 10 times. And I want to print out the value of I every time the loops run. So I will type this on my component so you can see how this works. I will open a new component. Let's write a for loop. For brackets and curly bracket. I always open and close my brackets every time I open one because it's a common bug that you forget to close when you have pieces of code very long. So I open and close immediately, so I never forget to close my brackets. So I will start initializing my variable of counting. It will be I, and it will start in 0. The I will be smaller than 10, and I will be increased by 1 per each iteration, right? I will be equal to I plus 1. This increasing a value by 1 is a permanent use function here in coding in general. So there is a convention to don't overtype this type of common codes, small codes. And the convention to add 1 to a count is just to put the variable you want to increase in 1 and plus plus. This means the variable will be increased by 1. But if you don't feel comfortable with this convention, you can just write I equal to I plus 1. I will use the convention here. So for every time I'm looping, for every loop, I will I will print out the value of I. Okay, so I will use my command print, and I will print my value of I. But what happened with I? Print is a command that gets out of my script a string, a bunch of letters. But I here is a number, right? So I need to transform my number to a letter, to an element called a string. So for doing that, I just need to use a command. Here you just type it. Later you can check it in a Rhino command library. But to transform any value that is not a string into a string type, you use dot, the variable dot, this command to string. And then open and close brackets. This means that the content of I will pass into a string. Perfect, we are done. So what's going on here? Okay, there is a typo error to a string. Perfect. Perfect. We are not using the inputs, so I'm gonna remove them. I will open a panel. And look what we've got. We've got 10 different elements because we have printed out the value of I every time the loop iterates. And we have defined that the loop will iterate 10 times. So we have the first value of I is 0, then is 1, then is 2, 3, 4, until the last one. This is extremely useful. It's useful to extract or dive into the elements that are stored in a list, for example. So you can take the index, the I as an index of an element inside a list and extract this element outside the list. Okay, here, perfect. We are okay with this. I know it's tricky and that you have to get used to this, but don't worry, it's a syntaxes that you need to memorize in case you are gonna dive into coding more. And as much as you practice, the better. So, okay. Then after the for loop, there is another type of element that I want to present you. And these are lists. Until now, we have seen how variable can store one type of data, one data. like A store a value of 5, okay, like a string store like one sentence. But lists are a type of variable that can store a number of data elements inside its content in a specific order. Like, for example, like it stores the information like a list. There is an element number 0, element 1, 2, 3. If you work already in Grasshopper, you know what lists are. So this is a way to create a list inside our script component. This is one of the most complex syntaxes from all that we are going to see today. Don't worry if you don't remember this later. I'm going to type it with you. But this is the explanation of the syntaxes. First, we are going to, as usual, say the type of the variable we're going to declare. That is a list. We're going to declare a list. Then inside a larger and smaller symbol, we have to put the type of the data we are going to store inside the list. Because it could be a list of numbers, it could be a list of words, it could be a list of decimal numbers or integers or whatever. So here you have to say, okay, it's going to be a list full of strings in this case. And my list is going to be named my menu. But here I just declare the variable. I haven't actually created the list, just the variable my menu. And how I initialize this variable as a list, I put the same command that went in a point, equal new list. I have to remind the computer here that is a list of the strings inside a smaller and larger symbol, and then bracket and bracket, open and close bracket. I know it's long and complicated, but don't worry, this is something that you have to memorize. As the more you practice, the better. So the brackets means that it is a list that contains something. At this moment, when you initialize the list is empty. So why there are some curly brackets right after my normal brackets? You can use the curly brackets to start adding elements to my list. At the beginning, I have a list that is called my menu and is empty. But if I follow my normal brackets with curly brackets and some content, I will start filling the list with some data. In this case, I have filled it with 2 strings. One is entrance and the second one is main course. What's the benefit of using lists? We can store many number of data in one variable, but we can also manipulate the information inside. We can add more elements to my list or extract some information from the list. We're gonna do this on the Grasshopper plugin. So the C# component. So let's go in, and I'm gonna just pass the same data. I'm gonna write that is a list that will be full of string. Sorry. And it's gonna be called my menu. And I will initialize it, new list of strings that's empty. Perfect. So I could leave it empty, but now I'm gonna fill it with some elements that will be in transit. And main course. Perfect. So now we can extract the list outside my component, saying just A is equal to my menu. Okay, and if I put panel in A, we can see that we have a list of 2 elements, one in 0 position, one in 1 position, and they have an order. And what's the benefits of using lists? We can manipulate information. For example, I want to add another string to my list, and I can use this command, my menu dot add. This means that I will add a new value to my list. Bracket, bracket, and what value I'm gonna add? Whatever you want. Right now, I'm gonna add dessert. And if I put OK, we can see the value has been added. Perfect. So we have dived into list. And how we extract a value? Let's say I want just to extract the value that is in the first position, not the first, the position number 1. We can use this command, my menu, and use square brackets. And inside the square brackets, we can say the position of the element we want to extract. For example, I want to extract the element that is in the position 1. And I will assign this element to an output named B. Okay, I don't have a B output. I'm going to create it right now. And if I connect it here, let's see. Okay. The main course that it was in the position 1 has been extracted. And now I have it isolated. This is extremely useful to operate different elements inside a list in general, to extract elements, operate them with themselves, etc., etc. So I know the syntax of a list is very tricky, but don't worry. Practice will help you to memorize this kind of syntaxes. Okay, so we return to the presentation. This is what I was saying. Here, for example, I'm extracting the item in the index 2. That would be this one. Perfect. So now the third exercise will be creating a list of point 3D. And for that, we return to our canvas. I will create a new C# component just to record all the process. And how do we create a list of point 3D? Exactly as we did it before, list of what? Of point 3D. Be careful with the typo errors. It's very important, the capitalization of the types of the variables. This is like a law. And don't mistake that, please, because you are going to have errors. The syntax is extremely, extremely important. So my list of points is going to be called my points equal new. I will initialize it. New list of point 3D. And it's going to be empty. Okay. Now I'm going to create a new point. We already know how to create points, so I will create a point 3D that I will name first point. Okay, and it will be a new point 3D with random coordinates that I will set 0, 0, 0, the first one, and I will create 2 more, as much as you want, as many as you want. Okay, sec point. I have to change the name of the point because I already have a point called first point, and I will create the second and the third point. And I will give them, provide them with different coordinates, whatever you want, random. So I have 3 different points. Perfect. So how do I insert these points into my list? Using the command add that we saw before. So my points dot add, and inside parentheses, what I want to add. I will add first point, and then I will repeat this action a couple times. Secondary point, third point. Perfect. And I'm gonna extract my list from my script, just assigning the output, the value of the list. My points. So A, my output, will share the information that is on my list. I'm sorry, is okay? Yes, okay. And there is a typo error here. My points. Perfect. So I will turn off all these previous components. So now I have extracted my list of points. So I can plug a panel and see all the coordinates, and now I can see them on the Rhino canvas. Perfect. So now we are going to add one more level of complexity in terms of using statements. What about if you want to create 100 points or 1,000 points? Like, you're not gonna declare point by point, point by point each time. Is pointless. So we already have a statement to repeat a code a number of times. That is my for loop, right? We already saw the for loop. So now I'm gonna use a for loop to create a bunch of points, a large number of points. And we will see how a for loop is very useful for this purpose. So for, I will open and close all my brackets, and then I will declare my count variable in I equals 0. Then, okay, how many points I want to create? It's smaller than, I don't know, 100. Okay, and then semicolon and I plus plus to increase the value each time. And I will create my point here. Point 3D. My point. Point 3D. And I will put 0, 0, 0, a random coordinate. And then I will add it to my list of points. My points, add my point. Perfect. So now I have this operation. This code will run 100 times, and every time it creates a point, it will add it to my list. So what happens if I put OK? In the canvas, I cannot see them, but I cannot see them because all of them have the same coordinates, right? 0, 0, 0, 0. I have 100 points, all with the same coordinates. What if I want to see them? I want to change the coordinates per point that I created. Here I'm gonna use this very useful item that is my variable I. My variable I is the counter of my iteration. So the variable I change every time the for loop runs. So I will use the value of I to create my points as a coordinate. So like using my variable I, every time I create a point, it will have a different coordinate than the other. So what happens if I put OK? I have an array of points that have changed its coordinate per iteration. As you can see here, you can see the coordinates, and here you can see in the three-dimensional space all the points. So with a simple for loop, I create 100 points without necessity of declaring 100 points per separate. Okay, so now we have mixed two different statements. This is great. But for loops are more fun than what you think. For loops are a very interesting function because you can put a lot of for loops inside other for loops, right? You can nest, this is called a nested function. You can nest a for loop inside a for loop. For example, what happens if I want to create a grid of points, not an array of points? I can use a nested for loop. So now we are going to create a grid and not a single for loop with a double for loop. So I will explain what is going to happen in terms of mechanical operation of the code, you know? How the computer computes this part. So I have 5 iterations of I, right? I have defined here 5 iterations of I. So my I will change of value 5 times, and I have them here down below the grid. I0, I1, I2, I3, I4. And if I nest a loop inside my for loop of I, and I put in another variable because I already use I, so I put in J, that is the convention. You go alphabetically from I to the rest of the letters. You can put the name you want if you don't like J. If I nest a for loop inside my for loop, this means that for every time I has a value, another variable will be initialized and will change 5 times. I know this is hard to understand at the first, but I'm going to try to explain it. If not, you can revise this tutorial several times on YouTube. So what happens is that when I is 0, I will execute a for loop that will define a variable j, and it will change a value 5 times. And when it finishes in 4, that is the final value of j, then we go up again to the first for loop, and I change a value from 0 to 1. And then I run the second for loop again 5 times, and then when it finishes, it changes the value of I and run it again. This is what happens. And what nested for loop provides us? Provide us with 2 variables that are consecutively changing of values in a nested way. This means that I is 0. I have nested 5 different values of j. So to be easier, I'm gonna script it on Rhino, on Grasshopper, so you can actually see what's happening. I'm gonna copy this component. So we already have a for loop here that is creating 100 points using the value of I. But what happens if we nest a for loop here? I'm gonna just copy this, and I'm gonna close the brackets. This is extremely important. The function is closed. I cannot use the same variable. It has already a value inside this function, so I'll change it for j. Okay, so now I have 2 variables that are constantly changing, and I'm gonna use one per coordinate. X is gonna be the value of I, so every time I change, it's gonna the point will change of position in horizontal. And I will assign the value of j to the y coordinate. So every time j change of value, the point is the created point is going to appear one distance up. Okay, I will put okay, and we will see what happens. This happens a grid of points, because every time I is 0, I change j value 100 times. So the coordinate of the point changed 100 times, like in a row. And when I finished, my I value changed. So I create a point right here, and I start again the loop of j. I know this is tricky. You can revise this several times. You can repeat this code many times until you get used to. And this is it. And this is a very fun proceedment. We will reduce this so it's easier to see to 10. Okay, so here we have our 10 per 10 grid. Perfect. So we have gone through 4 loops. And before going to the exercise today, I'm gonna show you how you can nest more for loops. Obviously, you can nest another for loop inside the for loop. You can do this as much as you want. But I want to show you what happens if I create a third variable changing inside my 2-degree for loop. And I will assign this new counter value that is permanently changing to the z coordinate. Okay, let's go around 74. Okay, I haven't closed my brackets. That's the problem. Okay. Perfect. So now that we are in top view, we cannot see it. I'm gonna turn this off. But if we go to perspective, we have a beautiful cube. Because now it's a third grade nested loop, so it's not only changing in X and Y, it's also creating a point when it changed in Z. You can play with this a lot. You can get the distance from these points, play with colors. So I encourage you to keep practicing these for loops. Perfect. So we are going to move forward. Okay, this is an exercise that I want you to try. I'm going to go very fast through this because if not, we are not going to have time to finish the tutorial on time. So this exercise will aim to subdivide a curve to transform it from to be very sharp to very smooth. So this is what's going to happen. We are going to have a list of points that will construct a polyline. And then we are going to start subdividing the segments until we have the smoothness, the desired smoothness, but keeping the direction of our segments, obviously. This is called, we will going to use the Chaikin subdivision scheme. So it's a mathematical proportion that is being already set by Chaikin. So don't worry, you can research about this and understand more, but for now it's just going to be a formula that you have to copy. You don't have to dive into that much. So what we need to start this, we need a list of points that are our initial points, right? These ones, the first points. And also we want an input of iterations. We want to know how many times we want to divide until we are satisfied. We want to control that the amount of divisions we want. So we're going to start for that. We are going to turn this off. And we are going to start the exercise from 0 now. This is a very good exercise to understand how can I control the action and reactions inside my script or with my script. So I said that I needed a list of points that are my initial points. I will put I or initial points. And this won't be an item, right? This will be a list. So be careful. Here you don't have to just set what type of information you are gonna plug in. You also have to tell the computer you're not gonna plug an item, you're gonna plug a list. So let's do that. And here I want to control my number of subdivisions. So I will call that iterations. Iteration counter. You can put the name you want. I'm gonna use these names because it helped me to understand what information I'm plugging in. And as it's a counter of iterations, it's gonna be an integer. Perfect. So if you already work with Rhino or Grasshopper, you already know how to create an array of points. You're gonna go here, I'm gonna select multiple points, and I randomly gonna draw some points. Perfect. So I'm gonna store this in a component of Grasshopper. Right click, I open the point component, then right click and set multiple points. Okay, now I have all the points here. I have my list of points and I will plug them in. And I will plug a slider that will help me to control the number of iterations or subdivisions that I want for my curve. Perfect. So we get into this component. Let's return to the presentation. Okay, so we are gonna find, basically what we are gonna do, we are gonna find new points that will define my curve, right? We have an initial list of points, but we are gonna change that list for another list of points with different information. So for that, we are gonna create another list of points to store my new points. I will name it okay, list. It's gonna store points 3D, and it will be named new control points. I will initialize it, new list of points, and it will be empty because today at this moment we don't have any extra point or any new point. Perfect. So we are aligned with our presentation. So what we have to do. To subdivide a segment, we need to get 2 points, 2 consecutive points, right? Because a segment of a polyline is built by 2 points and that are consecutive. So we have already our list with points. that are in a list in an order, a certain order. But we need to access them. And for that, we are going to use a for loop. So we will run a for loop amount of time, as much times as the count of my control point list, my initial points list. Why is that? Because the variable I, the counter of my for loop, will allow me to extract as an index that will extract from this list the point that I want to test. I know it's tricky. Let's try it. So I will initialize a for loop. And I will say, okay, I will initialize the variable of count. I equal to 0, I smaller than, and here I need to run the for loop according to the count of elements inside my initial point list. So how I get that number, the count of elements that are in a list, we can use a command name count. So my initial list of points is initial points. And how I get the number of elements that are stored here with the command name count. Perfect. And then I plus plus. Okay. Let's return to our presentation. So here I have highlight the times this for loop will run. Why I put a less one? Because we have a polyline and we are accessing to a point, and then with this point we are accessing to the next one to compare the distance and try to find the secondary points. But what happens if we take the last point of our polyline? If we go to the point here, number 7, for example, the function won't run because it doesn't have another point to test with. So we have to just take until the point 6. That will take 7 and we'll calculate intermediate points, but not the 7 because the 7 doesn't have any other point to test with. So for that, we will run this for loop until the previous point to the last one. We will reduce the count just by 1. So we guarantee not to take the last point of the list. Perfect. Now we are gonna find the intermediate points. The check-in theory says scheme. The check-in scheme says that for smoothing a curve without losing the direction of the segment, we just have to find these 2 intermediate points, one at 1/4 of the distance and one at 3/4 of the distance of the 2 points, and add it to the new list. So we have this kind of effect. So now point number 1 and 2 are the 1 and 3rd quarter, and we start connecting them with a new polyline, right? And we can do that many times. So this is a question. It's a vectorial operation. What check-in says is that if you sum both positions, the 75% of the first position with the 25% of the secondary position, we are going to get the 1/4 position. So we are going to have the point at 1/4 distance. And if we do the same, but in the opposite, like the 25 of the first and the 75 of the last point, we're going to get the 3/4 position. So this is something you can research later. We're just going to copy it on our component. So I just want, I will create a new point on 3D that is going to call 1/4. I will initialize it, new point, 3D. And I'm sorry, I'm not going to initialize it because I already have the points, okay? I have the points in the list, the points that I want to operate. So what check-in says, that is the 75% of the first position. How I access to the first position is my initial points list in the index I. That is how I access to every element of my list, right? Because I will take first the 0 index and the 1 index, the second index, like this, repeat all the time the for loop is running. So, and I add this to the 25% initial points. And here I will take I plus 1 is the next point of my list. Perfect. And my third quarter, I'm gonna make this bigger. This is my 1 quarter point. The third quarter point will have another name. And it's gonna be exactly the opposite. Perfect. Now I have found my 2 points, my 2 intermediate points to smoothen my curve. And what I have to do now is store these points into my previous list, the list that I create for the new control points. So I will use the command add new control point. This is a list that I have already declared. And I will add first 1 quarter. And then I will do the same with the other one. There is a typo error here. Perfect. So and now I have a list that store my new points, but this has just run for 1 time. The for loop has just passed for all the segments once. What happened if I am not satisfied with just 1 iteration? Like here, for example, this one is the first iteration of subdivision and I'm not happy. I want it to be more smooth. So I need to iterate another time. And that's why I have an iteration counter. So I will nest all this for loop into another for loop that will run the amount of times that I can control through my iterations. Let's do this so you can understand this better. So I have an integer that is named iteration counter that will set how many times I have to subdivide my curve until I'm satisfied. So I will nest all these functions into a bigger for loop. Open and close. I have to use another variable, so I will use j. J is smaller, always is smaller than my iteration counter. And then j plus plus. Perfect. And now we only have to, oh, there is a detail here. So I have this list of new control points. But in next iteration, when these new control points, I want to keep subdividing this, I have to pass this information of these new control points to my list name initial points. If I don't pass them, okay, it's gonna take the initial points of the beginning. So I need these new control points for the next iteration are the initial points. So for that, I will just pass the information through lists. So initial points will be equal to my new control points. Okay, this is, as I explained it, so every time I iterate this for loop, I keep subdividing my previous result and I don't return to the first result. So I will output this list of initial points. And okay, let's see. Okay, there's a typo error in line 64 and 65. Okay, 21 quarter. Okay, I will copy in. No. Okay, yeah, here. And I have the same typo error. So this is the good of C#. It brings you the problem. And line 65, there is still a typo error here. Perfect. So what we have? We started in with these points. I will plug a polyline. See how it's being subdivided. Then next iteration, we subdivided that first one, taking the 1/4 and 3/4 point, and we interconnect all of them. But I'm not satisfied. I want it to be smoother. So I pass to the next iteration. I take as my initial points this curve with these points. I pass the information and I keep subdividing until I'm satisfied. Okay, perfect. This is how we are learning to control actions and reactions. So depending on certain distance, we are subdividing, we are creating smoother curves, we are adapting our initial design to our criteria of what is enough or satisfying. So sadly, I will have to go faster. There are some things that we won't be able to code together because of time. But you can revise this tutorial as much as you want for later exercise. So here, there is one of the images I share with you in Instagram for this workshop. So this is how I can use this function for other types of, other situations. I will go to, you have already these files, one called outputs and one called tutorial guide. In tutorial guide, you have all this process already in the plugins if you want to open them and see them in advance. I'm going to turn this off. This is not what we are doing now. So here I am using the subdivision curve function inside a bonoroid, a three-dimensional bonoroid. What I did was to just draw a three-dimensional bonoroid that divide me this square in several bubble spaces. It provides me with a bunch of curves. I will turn this off. And I'm using the function that we already coded of subdividing the curve many times to get a more smooth result in the corners. So I ran it 4 times. I recorded the iterations with this component. I just piped them so I can see them in with a thickness. And this was the result. So you can play with this code as much as you want in your three-dimensional space with other type of formulas or whatever. So, okay, this was a little example of what you can do with this. So here I have to go very, very fast. I'm sorry, we cannot stop in the code anymore. Randomness, I'm gonna explain it just verbally. I'm not gonna run. Or maybe, yeah, we have time for the one. So randomness, what happened with randomness in computing or in computers? We cannot, randomness doesn't exist for computers. Computers just execute orders and they cannot say, okay, I will randomly pick 1 or 2. They are electrons, so you just need to give it an instruction where to stop to select a number. So what happens here, there is a function that every random component has that use a number that you have to provide that is called a seed, the famous seed, from which it runs a function, a mathematical function that provides you a bunch of numbers that seems to be random. They are chaotic, but they are not actually random because they are a product of a mathematical formula. And if you don't provide this seed, it can assume a preset seed, like, for example, the random component in Grasshopper. It always comes with a seed input that if you don't plug your own seed, it has the number 2, I guess. But inside coding, if you don't provide the seed number, it will take the clock of your system That's why you always have different results. So this is just for you to know, like curious data. So how we get random numbers inside coding? We have to initialize a new type of variable. This is a variable that will generate random numbers. So that's why I always name it random generator, because it's not a random number. It's a variable that will generate a random number every time that I need a random number. So how what is the syntax for this? We start obviously with the type of the information my variable will store, that is a random generator, and that you can write just random. Then the name of my random generator, that is my random generator in this time, very literal. And then I will initialize it, and I will put just equal new random. It's like a new random function that will provide random numbers. And what happens if I want a random number? Because now I just have a random generator, right? Okay, I will create my variable that will store this random number. In this case, it's a double that will create a double name random number. This is the name that I decided to put it. Equal, and this is how I generate a random number. I put the name that I've given to my random generator, in this case, my random generator, and I put dot next double. That means that, okay, this random generator generates a bunch of random numbers, right? So next double, what means is give me the next random number of the list of random numbers that you have generated. And parentheses, brackets, and close the statement. This is another type of variable, so it has another syntaxes. I'm sorry if it's a lot of information, but you can revise this later. So this is what happens. Here, for example, I have used a for loop to generate several random numbers. So inside the for loop, which runs 10 times, I have I have created a double named random number, and I have initialized my my random generator to give me a double every time the for loop runs. So I have these 10 random numbers. Another characteristic of generating random doubles, in this case is a next double, is that they always are in the range from 0 to 1, as you can see. They are all decimals from 0 to 1. If you want to have another range of numbers, double numbers, you have to later scale them to a new range, remap it to a new range. You can also generate random integers. In this case, it allows you to create your range. In this case, I put from 10 to 20. So my numbers are my random numbers are integers from 10 to 20. So how I scale my doubles? My doubles are the problem because they are from 0 to 1. There are many strategies, but mostly are simple mathematics. In this case, for example, if I want a domain between 0 and 40, I just have to multiply my numbers per 40. So if I have a random number 0, I multiply it by 40, my result is 0. And if I have my double 1, I will have 40. So I scaled the domain between 0 and 40. What happened if I wanted between not 0 and another number, I wanted between -3 and 3? There is a bit more of mathematics in this remapping. This is the formula. Basically, if I wanted between -3 and 3, I will have to multiply my random number by 6 and subtract 3 from each one. So this is the reason, the formula that is written here. You can revise it later, but this is the logic. I will multiply my random by the subtraction of the maximum and the minimum, and then I will add the minimum. In this case, is negative. I will have a positive multiplicator, and then I will subtract the minimum. Okay, I'm sorry, this has been very fast in terms of explaining the syntaxes of randomness, but I will go to the canvas to create to do the exercise, that is generate a random number of points so we can execute this formula. I will go to my class file here. C#. Perfect. So I will initialize a random variable that will be named my random generator or random generator equal new random. Perfect. I will just check it out. Yeah, it's okay. So now I will create many points, right? So I will use a for loop. So I don't have to create the points one by one. Int I equal to 0, I less than, let's say 10 points. Okay, and I plus plus. Perfect. And here I will create 3 random numbers. Okay, so it will be double x, that will be a random number, random generator, and I will put next double, brackets and brackets. This means that give me the next double that you have generated. But I want it between 0 and 40. So we will multiply. And I will generate 3 of these, because my points will take 3 coordinates. So I will generate randomly 3 coordinates. And now I will create a point 3D. Name my point for new point 3D. And I will use my coordinates, my random coordinates, Y and Z. Okay, but I have 10 points. I haven't created any list to store them. I will list of point 3D, my list, then new list of point 3D. And it's going to be an empty list that I'm going to fill every time I create a point here. Okay, so I just have to add the points to my list. So the next step is list, add, and what I'm going to add, my point. And I'm going to extract this list through A, that's my output, my list. Perfect. So we finished. There is a conflict here because there are some variables declared outside. So I'm gonna call them, and I will see all the points that I have generated randomly, right? Let's see them. I will turn this off so there are no confusions. Okay, I will store the data. Perfect. So I have them in the space because I have defined a set of random values, so we can see the points in the space. So I want to create a external variable to control that it will be count. I want to control the amount of points that I'm creating, and it's going to be an integer. This will, I don't know, put a random value. I will create, I don't know, 120 points, a lot of points. Perfect. So I want to run this for loop, the same value of count. So count here, yeah, I have 120 points, and I'm using an external variable in my operation. If I want less points, what happened here? I haven't provided seed value, so every time I iterate, it's taking my clock of the system, and that's why the points are moving. But I can provide the seed that I want right here. So I will put 2. So now you will see that the points doesn't change of position, just of amount. If you want to change the position, you can also extract the variable of the seed. seed can be an integer too, and we can put it here. There is no seed. So we connect. What's the problem? Okay, 61, 61. Maybe this should be a double. Okay, we can forget about the seed for now. It's not really important for today's calculations, but we can check later in Rhino Common what's the correct syntaxes to apply the seed for our calculation. Okay, so now we can create random infinite points. Perfect. We are in time now to compute or type the next exercise. That is, well, this is what we've done. And this was the main objective of the tutorial. I wanted to reach here, but I think it's gonna be too long. So what I'm gonna do, I'm gonna explain all the process of this exercise of circle relaxation. And then later you can revise detailedly all the script, and you can type it yourself. If you also have you have access to the files of the course, there is a file named tutorial guide. So here we have the points relaxation code, so you can get in and follow step by step. Later, but I'm gonna go through this faster. I want to stop in every decision because it's gonna take too much time. Okay, and why is this important? Because in here, as we can see in the image, there are not just only random points spreading in random directions. They are agents of a list, and they are calculating what's happening in its environment. They are calculating the distance with other agents like it to take a decision to where to move, to get away from all the points that aren't according. I'm sorry, that they don't have the correct distance that you have set. In my case, I have define a distance, a minimum distance to that will separate these points, a minimum distance that they should have actually. And you can see in the image that they are not only getting away, they are getting away from everyone that is too close, but they are stopping when the condition meets, when you achieve this minimum distance. So there are a bunch of decisions that these agents can take. And this is what we call, that we design a behavior of elements. Here I am not designing how this output will come out, and how is the final shape of this bunch of points. I'm just designing how they should move, when they should move, and how they can calculate the motion actually. And this is why we call this generative behavior design, because it happens through iterations, and we are coding a behavior. Okay, so after this introduction, we will dive in the complexity of this code. Here, I wanted to explain you about the characteristics of a persistent variable. This will allow you to don't initialize a variable every time you run the code. So you can store data every time you initialize the code. So for example, you make one calculation and then you say to the program, okay, calculate again, but you give a result. So you don't have an internal for loop. You finish all the code in the private void run script. and you extract that value. And you want to iterate over that value, so you can use what is called a persistent variable to store that data you want to be persistent through the new iterations. This is way more complex. I won't go through this because we won't need it for the exercise. But later I can share with you this material so you can revise it. Okay, and with here I wanted to make a dynamic point exercise that will make the point to change of position permanently, move permanently. I can share with you the material so you can revise it later, but it won't be essential for our circle relaxation scenario. So let's get into this directly. So we have a bunch of points, and these are the general aims for the exercise. So each point of my list needs to calculate the proximity with other points of the list, okay? And not only calculate, we need to store the data of each collision, right? From each one who is too close, that is violating my distance law. And also, after all the testings I do through the points of my collections, I need to calculate an average vector to move away from all those points that are colliding with me to satisfy all of them. So in this case, I have A, B, and C that are colliding. And for example, A has to calculate the vector to get away from B, and the vector to get away from C. But I shouldn't move in the direction that satisfies C or B only, right? I have to move away both of them at the same time. So for that, I need to make an average between these two vectors that I calculate first, the vector that I calculate for getting away from C and B, and make an average to get a final vector that will tell me the direction and the distance that I have to move away to accomplish my distance minimum requirement. Okay, and finally, I have to execute the move. I will follow my code with a pseudocode that is my instructions, but written in English, so you can understand the steps that we are taking when we construct this algorithm. The first I'm going to do, I want to show you this because it's a very good practice that I always do on my codes. When I insert a number of values into my code, a list of data, I normally pass this to another list with another name, so I don't have to operate directly with the information that comes from outside my code. You don't have to do this, but I find this a very good practice because I don't mess around with information. I just work internally inside my code. So what I did here is to create a list of initial centers that is going to call positions. And position will store all the information of my list starting position. That is what I'm going to plug in, all these initial positions that I'm going to plug into my script. It's a list of positions, of points in 3D. Perfect. So, and also what I have to do, I have to set the permitted distance, the minimum distance the centers or the circles should have so they don't collide. And this distance, I will define it as 2. Okay, you can put the distance you want, but here I put 2. What's the next we have to do? This is a bit tricky. We have to access to every point of my list of starting positions, of starting points, and make this point, to calculate its distance with all the other points in the list. And I will do this with a nested for loop. Okay, so every time I take a point in the position I will test this point in the position I with all the other points in my list. And these other points in my list will be defined by the variable j. Here I wrote the nested for loop. And what I don't want to do is to have to test my position with me, right? I am also in the list to be tested. So I don't want to test with myself, with the point that I'm pointing in I don't want that j takes the same point and calculate the distance because it's the same point. So to avoid that pointless calculations, I will say that j will start always at I plus 1. So I never take I as in the point named j. Okay, I know it's tricky, but this is what's happening. So I will test its distance with I plus 1, I plus 2, I plus 3, I plus 4. But what I don't want to do is test I with I, because it's the same point. So to avoid that, I will say that my testing point won't start at the same point with where I am starting. Will start one position more. So this is what will happen. Okay, I have my 2 points selected, my point I and my point J, and I have now to calculate the distance between to see if they are too close. So how I calculate the distance between them, I will use a command that you can see in Rhino common named distance2. So I will define a variable d that will store the real distance that exists between these 2 points. And this distance will be equal to the point in the list center with the index I and its distance with the point in the list of centers with the index j that is different. Okay, so that's how we get the distance from a point to another point using the command distance2. Okay, so when we get, I know this is a lot of maths, so don't worry. This is probably the most difficult piece of code we're going to see today. This is the last one. So let's move over this. Just can revise it later, step by step. So what I have to do now that I have the real distance? I have to test it, right? If this distance is appropriate, if it is violating the minimum distance. So I will use a conditional that says what? If my value of d, that is the previous distance, my value of d is larger than the permitted distance, I will continue, because if the distance is bigger than the minimum, I don't need to do anything else. I don't need to get apart this point. It's very far away, so it's okay. So we continue the for loop, checking the next pair of points, okay? So that's how we use the continue word. If this condition is true, perfect, let's estimate whatever whatever code is below and check the next point. You don't have to do anything if the distance is bigger than the minimum. But what happens if not? If they are colliding? In this case, I and j are colliding. So what we have to do? We have to find a vector, the vector to move I away from j, and the same, j away from I. And this is pure vectorial operation. This is pure mathematics. So if you don't remember vectorial operations, don't worry, you can revise it later. It's not something we use daily or permanently, so it's okay if you don't remember it. But to get this motion vector, we need 2 data. We need the direction of the vector and how long is this vector, how much we have to move away from the other. So to get the direction of the vector, the mathematical operation is just to subtract both positions and you will get the direction you want. Perfect. So we define a vector named motion vector that will store the direction of the vector. And we have it subtracted centers in position I with centers in position j. So that's how we get the direction. But this vector has a distance that is not necessarily the correct. Now we have to give this vector the correct distance. How we do that? First, we're gonna use the command unitize that will transform this vector in 1 unit of distance. And later we will scale it to the distance we actually need. So first we unitize this vector that is a direction. Let's, I will try to draw here so I have this vector, sorry. that we don't know what is the length. So what I'm gonna do first is that I'm gonna convert this vector to 1 unit I don't know, like this, I will say, okay, keep the direction and let's make 1 unit of length. And now I have to calculate the real distance I need for moving my point, right? How I got this? I got this using this mathematical operation. You can comprove it in paper, you can do the math calculation later, but actually what I'm doing is subtracting the minimum distance with the real distance. So like that, I'm gonna get just this distance. That is actually the only distance that I need to get away to have the correct minimum distance from each other. So, okay, I have already this distance here. This is the new distance. But I don't want 1 point to take all the distance. I don't want 1 point to get away from the other, just one. I want both of them to get away from each other. So I cannot provide this motion vector the complete distance. I will just provide them the half. So this vector is half of the distance I need to get away from J, because J is gonna take the other half, and if they both execute the operation at the same time, they will be away from each other. So what I'm doing here basically is getting the distance that I need for the vector and taking just the half. And I'm multiplying this motion vector by this distance. So now my motion vector has the correct distance and direction for the motion. I know this is a lot of math. Please revise it with patience later. Okay, so then what else we need? We are going to do this operation per every pair of points in my list, right? Not only with J, we will do it. J will transform in point number 1, then number 2, number 3, and we don't know how many collisions we are going to find. So this vector needs to be stored somewhere. So we can keep storing all the collisions. And at the end, make an average to have the real movement, like here, for example. Here, like I found 2 collisions and make the average, and I got the true movement. Here, until now, we have just only find these single vectors, a vector per collision, but later we have to do an average. So how we store these vectors that we are finding and these collisions we are calculating? Very easy. We are going to create a list of vectors that will store the motions. So what we are going to do? This list of vectors has the same slots than my list of positions. And each position will correspond of the amount of vectors, of the amount of collisions and vectors that we are calculating according to the collisions. So what we are going to do? Our for loop to calculate the motion vector is testing position A here, with each one of the other positions in the list. If we don't find a collision, we don't do anything, and we pass to test the next position. But what happens if we find a collision? We have already calculated the motion vector, right, to get away from this position C. So we are gonna store it in the list of motions, of vectors of motion. But we are not just gonna add it to the list like another item. No, we are gonna sum it. We are gonna make a vectorial addition. So what we are gonna store is the addition of all the vectors we have to consider for our average movement. This is because to make an average movement, we will need to add sum all the vectors and then divide it by the amount of collisions. So it isn't efficient to store every vector independently. Every collision we find, we can start making vectorial additions. So here, for example, let's say that position D is not colliding with me, so we pass to position E that is not colliding also, but F is colliding. So we calculate the vector of the motion and we make a vectorial addition to the list of motion vectors. And like that, we can continue with position B, position C, or position D. Perfect. So I know this is complicated. Be patient if you don't get it. So what I'm doing is, first I'm creating very up in the code the list of total motions. Here, this is very important. I will initialize my list of vectors that was empty. Right here, I create a list of motions that is empty, totally empty. But then I want it to have a neutral vector to start making vectorial additions later for every vector that I find in my motion operation. So I will add per every center count a vector in 0, 0, 0 with no direction, anything. So to this vector, I will start adding the vectors that I will find later. And the other thing that I have to do is to every vector that I found here, after all this calculation here we find the correct direction and distance of the motion vector, right? Now what I have to do is to add it to the our list of vectors here. So the only thing that I did is like adding this vector to the correct position on my list of motions, of total motions, for I and for J, both of them, because both of them needs to move apart from the other. And since J has to move in the opposite direction to I, the motion vector is in negative. Please take your time to revise it later. This has total sense. And if a vectorial operation confuse you, don't worry, just you have to practice this. And we are gonna see this later in the code. Okay, now I'm gonna do this for making this vector average to get the motion, the real motion that I need, not each one separately. I also need to divide these total motion vectors by the amount of collisions, right? Like a simple average. Like if I want to make an average between 3 elements, I sum them and divide it by the quantity of elements I'm adding. So I also need to store I need to count the amount of collision that I'm finding. And for that, I will make the same strategy like for the vector. I know this is a bit confusing, but I hope this gets clearer here. So I will continue with my testing. With B, there is no collision, but with C, I have collision, for example. So what I'm going to do is to create a list of counts. I will count the amount of collisions I find. So if I found a collision, I will increase my collision value per 1. Okay, then I keep testing. And if I find other collision, I will increase my collision value again per 1. So now I will have a list not only of the vectors that I am finding, also of the counts of collisions that I'm finding in my for loop. And for that is the same strategy. I create a list of integers that will store my collision count. Then I will initialize a neutral value because at the beginning, I don't have any count. So every slot in the list of counts will be 0. And if I find a collision and I calculate a motion vector, I will increase this value, this collision value per 1. Oh, not only in I, also in J. So like this, I'm going to be able to generate an average vector. I know this is a lot of maths again. So if you're following this tutorial, maybe you just can copy this and analyze it later. But here, now we have already all the information we need to calculate our motion vector, right? We have a sum of all the vectors that are colliding with me, with each point, and the amount, the quantity of collisions that I found. So this is enough to calculate my motion. So I get out of this complex for loop, and I will start another just to calculate my average move or the vector that I need to move. So I start a for loop. I go through every center or every position of my list, and I will make an average between my motions and my count of collisions. For that, I will create a new vector 3D named average move, and I will do a simple division between my total motions and my total collisions, both at the same position in I. Finally, when I get my average move, this is my vector, my final vector. Okay, this is the final vector that says how much I have to move to which direction, because this vector should satisfy all my collisions, get away from all my collisions. The only thing that I have to do is to add this vector to my position, my current position. So like that, I am moving my point. I'm adding this vector to my current position to get a new position that satisfy all my collisions. So sorry for the bad drawings, but this is finally how we execute the motion. So we have this very large piece of code, but we don't want to move ourselves just one time, right? Because one movement probably won't guarantee that you are going to be away from all your collisions. Probably you will need to move away more than one time and more than once. We are going to do the same strategy that we did with the curve subdivision. That is that we will nest this big operation, all this operation from the lists of vectors and collisions to the finding of the vector, to the for loop to execute the motion. All of this, we are going to nest it into a for loop that will operate the amount of iterations that we want. So we can repeat this. We can repeat this operation several times in a controlled way. So here, what I did was create a for loop very up. I created a variable named iteration. As you remember, we can use any name as we want, I, J, K. In this case, I create one named iteration that will be similar to our iteration counter that we defined at the beginning outside our code. And we will increase it by 1 for every time of the iteration counter. And finally, we have to output our centers that have a new position. I know this is this has been very long, but I hope you can see it here. So let's return. Here I'm using the same random function we coded to get random points. I have generated 100 random points. And obviously they are violating the minimum distance we have defined. So what I'm doing, each point is saying, okay, which one is colliding with me, and is calculating the vector. I'm gonna draw it here. The vector to get away from each one of them. And after calculating this vector, is calculating an average vector to satisfy all that collision, get away from everyone. I'm just drawing something random here. But imagine this is the average vector. Okay, then I will execute the position by 1. Okay, and I move according to that direction just one time. But as we can see, we're still colliding. It's not enough. So we can run again the code indefinitely until I feel that I have satisfied my condition of distance. Okay, so this was the main goal of today exercise. This is a behavior, as I told you before. I didn't know how this was gonna come out. What I designed is all this piece of code, that gives instructions for my agents to operate and act and react to other elements in the three-dimensional environment. And this could be called a behavior because it's exactly like that. Some code or instruction of how to behave in case some conditions are met. So just to finish today's tutorial, I will show you how we can use this type of circle relaxation in many codes, as we did with the curve subdivision. I will turn this off. This is the first one. What I did was to draw airplane papers from paper, origami airplanes. And I have here my circle relaxation code. So here I have my iteration counter. And per iteration, the points move and the airplanes point in the direction of the average vector. So I can also extract the direction of the vectors and use them to make some cool graphics. So if I reset it, we can see this output. It's the same, but just add more components of Grasshopper. They're very simple, just maths and vectors. What else we can do? Here, there is something really, really cool. We already saw it in the publicity of this tutorial. Here I'm using the metable component and also a record component. This means that every iteration will be stored here. I will start from 0. So what does the metable? I have all my points here, as usual. What metable does is just to surround each point with a curve. But if they are too close, they are gonna just compile them into one curve. So here they are all too close to each other. So we have just one curve enclosing every point. But if they start moving away, the curves start to separate. So we have this cool effect of how a single curve can transform in many curves. And now we can see the points. Obviously, we can increase the iteration and keep them moving away. We could see the result. This is something very cool. You can experiment here with this code. I added some visualization algorithm. This is very simple. Don't worry about this. You can play with this as much as you want. And the last exercise or example that I have bring for you is to do exactly the same, but in 3D. Until now, we have worked in 2 dimensions. Okay, let's stop this. Yeah, perfect. So this is bidimensional. It's in the floor. But what happens if we provide the points with a variable in set? This is because all my points, my initial points, didn't have a set value. Set is 0. So all the vectors start to calculate each other just in X and Y. But what happens if we create points in the space? Like this. We are going to start having motion through the space in the 3-dimensional environment. So let's see. Let's reset this. Let's turn these initial points off. And in every iteration, they spread away. So now I did a very, very cool thing that is doing the same effect of the metable up here. But instead of enclosing each point with a curve, I enclose it with a surface. I use this plugin named Dendro. So it does exactly the same as the metable. So if they are too close to each other, they merge in one. And if they get away, they just separate it. And here, what I did for the presentation is just to slice them with horizontal lines. We are going to see this with a lot of horizontal planes, and that's how I got the final image of this tutorial. And we can keep separating them. Okay, then this is it. We will return. This is a small gift of the result. You saw this online. And I know we went through this final exercise too fast. Don't worry, you can recheck all the logics on the YouTube channel. And if you have any question or additional comment, you can contact me, no problem. And we can do this slow, more slow than what we did today. So thank you very much. And this has been Evolutionary Behaviors in C# Basic.
Thank you so much, Betty. This was such a structured presentation, such a structured tutorial, and it was so methodical that I feel like just jumping right into it after this session is over. I think if there are any questions from our Zoom audience, maybe you can just use raise hand or something, or just unmute yourself. But I'll maybe while they are thinking, I do have a few things which I wanted to just ask. So if there's anyone who's starting new with the coding, and especially in C#, because there are so many other platforms, there's Visual Basic, there's Python scripting. Would you suggest any kind of references, any books that they can refer to, or any good links that you would want to suggest, or your own links?
Okay, this is the first time I do a tutorial of coding. I have teach about computational design, but so I don't have many materials from myself, but I would like to highly recommend these tutorials of YouTube. I will share my screen. Long Nguyen has really good tutorials. Some of the exercise we practice today are from his tutorials. He works not only in C#, also in Python and other types of programming languages. So here we have a bunch of tutorials that are very well explained, also with subdivision, curves, meshes, and you can go from the very basic to the most advanced of coding plugins in C#. So this is a huge recommendation from me. Please visit this. You can also stop it, check the tutorials with your time. And inside this tutorial, especially these ones that are called scripting plugin development for Grasshopper, this is a conference. So you have all the material you need in here. All the information you need, papers that you can visit. So this is something I would highly recommend for those who are starting coding.
Okay. And any further readings based on evolutionary behaviors that you would like students to explore? Anything else you would like them to explore beyond what we did today?
Yes, let me share with the class the links. There are a couple of people here that do nice work.
I think we can share these links with our YouTube audience as well. Yes, but
there is this researcher named Alberto Giacchino. I will share a web page. He coded not only also evolutionary behaviors in not only in C# like us, he also does it in Python and in processing, and also in Java for HTML. So you can find interesting readings in his page, and also nice exercise because he has a lot of dynamic interactive elements to play with inside the web. But I will make a deeper research. I'm sorry, I haven't brought my list of readings. As long
No,
as I have them,
I think, yeah.
I will share them in the link of YouTube so you can access to them.
Yes, maybe that would be great. And if students want to reach you, could you just type out your email address or something for us? Yeah.
Yeah, of course.
Yeah.
Okay, I will type my email address and also my Instagram page, and you can write me through that.
Yeah.
And also my lab design, Ladove Design Lab is also open for your questions.
Yeah.
This is my email to everyone. My Instagram will be, and the laboratory page was at the beginning of the presentation. Okay, it's here.
I think we did have 2 questions from the audience, but I think just at that same time you addressed how to model in the 3D environment as well. So we had a YouTube question: if the points are in 3D, how this algorithm could manage the position? But I guess it was addressed immediately afterwards. And the second question we have is from our participant here, Isra. Isra, would you like to ask your question? I think Betty just provided the link as well for any of the other tutorials on multi-agent systems. Yeah, I think we're not connected, but yes, she was asking about
for more
multi-agent
platforms.
system tutorial.
Yes.
Yeah. Okay, so that brings us to the end of the session. I'll just very quickly give a reminder to our audience about the upcoming sessions and yes.
Hello, I'm Isra.
Yeah, hi Isra. Yeah, sorry. Yes, go ahead.
I was asking about applying multi-agent system in architecture. Are there any tutorials or references that I can learn how to apply them using C# and Grasshopper?
I'm sorry. I would recommend you, Isra, to check the page of the Bartlett School of Architecture, especially the architectural design program. If you are looking for examples of the how to apply this directly in architecture, like physical elements and interaction in this, I would recommend some of the works they have done in research cluster number 1 with Martina Rosati. I think they have experimented a lot of creating not only architecture, also furniture, stairs, using the interaction of agents. I can share, I will search for the specific projects and I will put the link in the YouTube channel so you can access to it. But in general, the RC1, the research cluster 1 of the Bartlett School of Architecture, they used to work a lot with coding, with agents and interactions to develop architecture. So I recommend that. I know that the AA also have a very good program that works with multi-agents for architectural development, but I don't know that as much as the Bartlett. So don't worry, I will post the links so you can access to them.
Thank you very much.
Yes. If there are no more questions, I think, yes, you're getting a lot of compliments up there. So I think you can check the chat, and I'll just very quickly summarize on the upcoming sessions. The call for papers for computational design and robotic fabrication workshop are due on 17th of January. We have our second in the series of Farsi session, Farsi language session on 21st of January. And on 22nd of January, Saturday, at the same time, we have New Hybridities Latin America session. And on 23rd of January, on Sunday, we will have our next in the series of doctoral consortium sessions with the Florida International University, hosted by Neil Litch. Details for this will be available soon on our Instagram page. And if you have any suggestions, if you want to connect with us, we're on Discord. Discord also has technical tutorial link, and we would love to see your outcomes from this session. So please keep us posted, and see you all soon. Thank you, Betty, once again. Thank you.
Thank you, everyone. Thank you, Mahavlin. Thank you, everyone, for Digital Futures. It's been an honor. Thank you for everyone to be here.
Thank you.